Hi everyone, thanks for attending this talk. Today I'm just going to update you on progress on revising the existing 3D geologic model of the bedrock of southern Ontario and our progress on development of a hydrostratigraphic model. The 3D model released in 2019 has been updated to reflect data corrections and to add improved model data rendering, some new enhancements, and an uncertainty analysis of model layers. There's also a virtual reality representation and 3D printed output. And there's related projects to map regional porosity permeability variations in the Lockport group with medical CT scans of select paleokarst intervals. 14 regional hydrostratigraphic units have been identified. These are to be represented as a 3D model suitable for numeric modeling of groundwater flow. As in the first model, project scope includes all the Paleozoic bedrock of southern Ontario, with 55 layers in the model representing 70 Paleozoic bedrock formations plus the Precambrian plus the superficial sediments, 1,500 plus meters of bedrock, 110,000 square kilometers at 400-meter resolution. This is a stratigraphic chart of the Paleozoic bedrock formations in southern Ontario. Is used to guide the stratigraphic coding of model layers. Model layers represent individual formations or grouped formations where necessitated by data quality, quantity, or thin formations. The erosional profile of the subcrop edges is represented on the chart, showing the frequent occurrence of carbonate capped cuestas. Of particular importance for groundwater movement are the occurrence of regional paleokarst horizons where carbonate strata were subarally exposed at erosional disconformities in the geologic past. This is a regional view of the new 3D Paleozoic bedrock geological model showing the bedrock formations coded in different colors and the legend for these formations down the side. There's 53 Paleozoic bedrock layers represented on here, plus the Precambrian was stripped off the superficial geology. Revisions to the model and new features include improved resolution of the subcrop surface and better correlation of the topography and bedrock geology of the Niagara Escarpment. Most anomalous outliers and structural and thickness anomalies and gaps have been removed. There's improved data quality and quantity for formations of the Lockport group. And new features and enhancements for this model include 3D extent of salt mining leases at Ontario's 2 underground salt mines, 3D solution mine salt caverns utilized for hydrocarbon petrochemical storage and for mining of salt, two-dimensional representations of oil and gas reservoirs and regional faults, and lithotectonic boundaries in the Precambrian basement. Principal input data were formation top picks for over 20,000 petroleum wells recorded in the Ontario Petroleum Data System. This is supplemented by stratigraphic test boreholes, measured sections, petroleum wells in Michigan, and control points. Digital files for subcrop geology, bedrock topography, Great Lakes bathymetry, and digital elevation model. And there's data for the model enhancements, including oil and gas reservoir outlines, fault traces, domain boundaries, salt lease boundaries, and sonar surveys of salt caverns. Regional faults are represented as extruded 3D planes at the locations of mapped regional faults in the Chatham Sag. This illustration is on the surface of the Middle Devonian Lucas Formation with all younger formation layers removed. This slide just shows the 2D representation of lower Silurian natural gas pools in the model. The formations shallower than the Cabot Head Formation and the Grimsby Formation sandstone have been stripped off. We've added a 3D representation of underground salt mines in southern Ontario. And this example here is in the Windsor area, showing salt mining of the F salt and the B salt in the Salina group. And also shown on here in orange are hydrocarbon storage caverns utilizing the B salt. An assessment of uncertainty in the model geologic layers is underway. This is new for this model. This was not done in version 1. This slide here just summarizes these sources of error that have been documented for the model. Data availability or sparsity of data is the main source of uncertainty for model layers. 3 examples are shown here. The darker colors show dense data, the lighter colors show a lack of data or sparse data. 3D printed output of this model will be available at a fairly limited size, but you can print the whole model or a small area, print text and labels on the model, combine layer packages. And for this project, we're using a Formlabs Form 3 printer. A virtual reality implementation of the model is nearly complete to create an immersive 3D experience for model users and promote geological education and public outreach. Model development requires that we understand the regional hydrogeological framework of southern Ontario and sources of groundwater data and hydraulic conductivity and permeability data, the geological controls on porosity and permeability development, groundwater surface water linkage and flow directions of groundwater. Need to understand regional hydrochemistry and a conceptual model of these zones of shallow, intermediate, and deep groundwater in southern Ontario, water types and origin, their hydrochemistry, and the isotopic data to identify their origins. Need to know the base of the fresh water, the shallow system, base of the sulfur water, and then we have to be able to assign the lithostratigraphic units to hydrostratigraphic units. Geologic features in the lithostratigraphic model relevant to hydrostratigraphy include regional structure, arches, basins, regional dip, faults, topography, erosional cuestas, salt dissolution, subsidence collapse features, and regional karst and paleokarst horizons. Development of a hydrostratigraphic model is supported by a variety of data. There's the water well database of the Ministry of Environment, Conservation and Parks. There's 160,000 wells that penetrate bedrock. The petroleum well database is, again, a principal source of data, just as it is in the lithostratigraphic model. We've compiled published hydraulic conductivity estimates, field observations, and drill core are a very important part of this process, and chemical and isotopic analyses, for example, from SCOOS and SCOOS ATAL. This slide just shows the location of petroleum wells in southern Ontario and their very irregular distribution, with some areas having a much higher density of wells than others. There are 3 hydrochemical groundwater regimes in the subsurface of southern Ontario. A shallow regime of predominantly bicarbonate-rich freshwater in the glacial and recent sediments at the contact with bedrock and in shallow karstic bedrock. An intermediate regime of brackish to saline sulfur and sulfate-rich water in paleokarst horizons at depths of approximately 30 to 350 meters, and a deep water regime of ancient evaporated seawater dominated by dense brines in paleokarst horizons at depths greater than 200 meters with up-dip hydraulic gradients. This is a visual representation of the previous slide displayed on a scaled geological cross-section of southern Ontario. Shown in blue are the shallow freshwater and yellow the intermediate depth sulfur water regime, and in orange the deep basinal brines. Water movement is down dip along paleokarst horizons in the shallow to intermediate regime and up dip along the same horizons in the deep brines. 15 hydrostratigraphic units have been identified as illustrated on this chart. HSU names are listed in the left column. The erosional profile of the bedrock formations is shown along the right. 7 of the hydrostratigraphic units are classified as aquifers. The remainder are aquitards or aquicludes. Colors for the aquifers are as in the previous slides. Freshwater occurs in 3 shallow water aquifer systems. 1 in the superficial sediments, HSU2, and a contact aquifer at the sediment bedrock interface, and HSU3 in shallow karst developed at the subcrop edges of carbonate formations. In intermediate to deep subsurface, thin aquifers of brackish to saline sulfur water or brine occur in paleokarst horizons developed at disconformities at the upper surface of carbonate bedrock formations where they were exposed to subaerial weathering in the geologic past. This table summarizes the named hydrostratigraphic units, their lithology, and the published hydraulic conductivity measurements for the hydrostrat units. The wide range of hydraulic conductivity values within some HSUs reflect the heterogeneity and anisotropy within each of them due to mixed lithologies, lateral facies changes, diagenesis, and depth from the surface. There is no diagnostic or cutoff value for determination of an aquifer versus an aquitard. Rather, it is the relative values and the recorded occurrence or non-occurrence of water within these formations as recorded in petroleum well records. The two related projects will contribute to our development of a hydrostratigraphic model. One is a geospatial and statistical analysis of porosity and permeability variations in the Lockport group. Interim results of this project will be presented later in this session. Another one of our related projects that is underway are medical CT scans of paleokarst and drill core. This will be specifically the Guelph Formation and the A1 carbonate. This is for 3D porosity visualization. The example shown here is from Silurian carbonates in Quebec, because we don't have results available to show you yet. So to summarize, we've revised and enhanced the existing 3D bedrock geological model. And to do so, we've included an uncertainty analysis that we didn't have before. There's new features such as 3D representation of salt mining, salt caverns, 2D representation of oil and gas reservoirs, Precambrian lithotectonic domains, and 3D regional faults. There's a public communication component with virtual reality representation and 3D printed output. We're developing a 3D hydrostratigraphic model with designation of 15 hydrostratigraphic units within a hydrochemical depth zonation of fresh, sulfurous, and saline brine groundwaters. Related projects include a mapping of regional porosity and permeability variations in the Lockport group, and a project to characterize pore geometry and connectivity for karst intervals in selected core using CT scan technology. This is just a list of references that I've cited in this presentation. You could come and look at these later. I'd just like to acknowledge the funding sources for this project, and I thank you very much for listening.